Yeah.
Hey everybody, welcome to Project Pegasus. We're super excited to finally get this out into the public and tell you more about it. Earlier this year, Ian Smith and I met to talk about the germination of the idea. Project Titan was a project that we worked on last year with Simon Verstraet and a small team of game artists that created this sort of futuristic Amsterdam-like city. And that was very helpful to the community. That's the feedback that we got, and we wanted to take that concept of a scene that creates a lot of learning material around it and shows how to use Houdini with Unreal Engine, and take that forward. So Ian and I met earlier this year and talked about what we could do around that, and the first concept was a sort of Scottish Highlands open world, and Ian was excited about taking that on. And building a team around that to create that vision. So, Ian, do you want to just quickly introduce yourself, and then we'll go around and introduce the team?
Yeah, sure. I'm Ian Smith. I'm a 3D artist based in the UK, and I work as a CG supervisor and a freelance artist, focusing on environment art for games. And so, yeah, I joined the project kind of very early on, got the ball rolling with Chris, kind of starting Project Pegasus and brainstorming ideas, and really was just responsible for directing the project over the last 7 months or so, and kind of contributing some of the learning material. So I started the initial block out for the environment and the landscape, and then went on to do a kind of a procedural cliffs and prop workflows, and really just trying to help direct the project and keep it rolling along the way. And it's prior to this, I hadn't really done that much in terms of like this bigger a workflow using Houdini on a real-time project. So it's been learning a lot of trying to build this kind of very interconnected workflow where everybody's workflow and pipelines kind of work together, and we can kind of collaborate easily using Houdini and Unreal 5 to kind of produce this very large, detailed environment. And then I think I'll hand it over to George to introduce himself and some of the work that he's been doing for Project Pegasus.
Hi, I'm George, and I'm a technical artist. I've been working with Unreal and Houdini for a fair amount of time now. And I was brought in slightly later on in the Project Pegasus development. I was the second artist after Ian. And my kind of main responsibility was to sort of pick up the landscape workflow from Ian and sort of take it on to its final stages. But I wasn't able to resist kind of letting my kind of passion for foliage and vegetation sort of sneaking in there and distracting me a little bit. So I'll say that I really enjoyed Project Pegasus because of how collaborative it was, and just how closely we had to work together. So there was really sort of a lot of passing of the baton to the next person when you sort of maybe reach the end of your kind of responsibilities or capabilities. So that was a really positive experience, sort of learning how to work that closely, so tightly on the workflows that we were using. For example, the foliage system was a tooling that kind of prototyped over a couple of weeks, and it seemed to be going pretty well initially, but then ended up kind of just hitting a bit of a wall and feeling like I was neglecting my other responsibilities. And Feike was able to kind of swoop in and basically take over that system and take it on to kind of become the eventual prototype that we used to build all of the vegetation for Project Pegasus. So yeah, I guess maybe Feike can introduce himself and tell you a little bit more about his role in the project.
I'm Feike Postmes. I'm also a technical artist right now in Tokyo, but originally from the Netherlands. I originally started working on Project Pegasus to deal with the architecture, but already pretty soon for when I joined, George had this amazing idea for a foliage system, which was very cool. But yeah, he had some hiccups, and then this was also, I'm not sure if we would have done this in a normal project, but we took a big risk, I would say, regarding this foliage system looks awesome. Let's just try it. Let's keep a tab on it for if we're wasting too many weeks. But after a couple of weeks amending it a little bit, it really took on shape. And as George already mentioned, it really did a lot for the project, which was really cool. In the end, I did a lot more for the Flora system than for the architecture, but still it was a really cool project to work with. And I also hope that Tillman, who actually used a lot of the tools, actually enjoyed it. But I think right now we're going to Alex first to tell him a little bit about himself.
Hi, I'm Alex Homer. I'm a technical artist also, and I recently graduated from a master's in game development. This project has actually been essentially my first step into the industry, and I've learned a lot about how professional creative projects are done and organized and working on such a fast schedule. I worked majorly on the clouds, where I could create a system, well, actually a couple of systems across a couple of different engine versions, which allowed true real-time volumetric cloudscaping in engine. And I also used the new Houdini 20 cloud tools to produce the entirety of the cloudscape within the environment. So handing off to Tillman to tell you more about Flora.
Thank you, Alex. I'm Tillman Milch. I'm a technical vegetation artist. I started out as a vegetation artist and just gradually slid off, like slippery sloped into the tech art business. And I was brought in by George into this project to be a vegetation artist and to work with these experimental tools. And I, in fact, did not enjoy using them a lot at first, but it took a while for me to catch on to them because they completely like threw off my conception of what vegetation art is. You know, it's like I'm used to speed3 or more conventional tools, and these tools really take like a simulation-based approach that goes into the nature of things more than the like phenomenology of things. And yeah, they forced me to sort of like rewire my mind a bit and rethink what I know about vegetation. And under a tight schedule and under the like expectation to myself to produce like production ready content, it was a massive pain. But the reflection afterwards and just realizing like what I have done in that time frame just brought me so much more than I could have ever asked for, you know? Like I always wanted to understand vegetation. Like I got kind of hung up in the tools. That's why I became a tech artist, you know? But I always wanted to understand like my craft as an artist. Like I think as artists, we understand like we drive to understand the world at its core, right? Like this is if you go back to Da Vinci and the roots, like where philosophy, science, and arts were kind of the same thing. And I think like as artists, we kind of like strive for this aspect of it, and this really brought me into this direction, and I'm really thankful for that. So yeah. Thanks everyone for your hard work, and I hope I wasn't too nagging in the process. And yeah, that's
well,
it.
It was a real pleasure watching the project come along and grow and prosper, and I'm really excited for today. So without further ado, let's jump in and watch your presentations.
Hello, my name is Ian. I'm the project lead on Pegasus. Over the next hour and a half, the team and I will be introducing you to some of the amazing learning content we've been producing over the last 7 months. The goal of Project Pegasus was to produce an open world environment that utilised Unreal 5 features such as Nanite virtualised geometry and Nanite landscapes to achieve a high level of detail. We want to show how Houdini can be used by a small team to produce such a large detailed environment. The world is a 4-kilometre island. The island is broken up by hills, rocky outcrops, and crisscrossed with dirt paths. Dense woodlands cover the lower valleys of the island, whilst the upper slopes are peppered with hardy vegetation. A small deserted village sits in one corner of the landscape, abandoned and overgrown. Project Pegasus sits somewhere between the need to research and develop new workflows that utilise new technologies such as Nanite, whilst also providing learning content for the Houdini community. I didn't want to limit the project to covering familiar ground, but instead present the aim of building a large detailed open world and tackle the different challenges that goal presented. Houdini became the solution to many of these challenges, providing a procedural and non-destructive workflow allowing a small team to iterate quickly, try and test new workflows and prototype tools quickly. I'll begin by introducing the Building a Collaborative Pipeline video series, which covers setting up a Houdini package file and breaking down our project folder structure. I'll then give an overview of how the landscape for Project Pegasus was created. George will introduce the Landscape Pipeline video series, in which he takes the base landscape and creates the incredibly detailed landscape you see in Project Pegasus. I'll then give an overview of how I generated the procedural cliffs for the entire island and some of the prop tools and workflows I developed. Feike will introduce the techniques he used to create digital assets that generate buildings from basic input shapes. And Alex will talk about how he created the amazing clouds that cover the Pegasus island. Finally, George and Feike will introduce the Flora tools, a set of prototype foliage tools that Tillman used to build the trees for Project Pegasus. We'll be releasing the content weekly over the next few months, starting with Building a Collaborative Pipeline, Landscape Creation, and Landscape Pipeline. The team has put an incredible amount of work into Project Pegasus, so thank you so much for joining us, and I hope you enjoy the presentations. To begin with, we're going to take a look at Building a Collaborative Pipeline. I wanted us to approach Project Pegasus in a holistic way, to not just kind of break down specific individual tools, but to show how Houdini can be applied to a game art pipeline. So this includes demonstrating how we use Houdini packages with our project folder structure to collaborate and share files whilst staying organized. If you are familiar with package files, they are JSON files that allow us to add custom directories to the Houdini path environment variable. The Houdini path variable is used when searching for HDAs, shelf tools, desktops, icons. So we as a team can store our library of custom digital assets in a folder within our project folder structure and have Houdini load those digital assets. It also allows us to specify custom path variables. So for example, if I just come to the package browser, you can see here I have my Pegasus demo package, and this sits in the documents folder. I have my Houdini 20 folder, and here I have a packages folder, along with an OTLS folder, a toolbar, desktop. So all these directories are searched by Houdini when Houdini launches. But if I come in here, I have a package file. And we're seeing some information here in the package browser. So if I right click on this package and open it up, I'm creating some custom variables. So I'm creating one called Pegasus Demo Project, and this needs to be a path to my Pegasus folder structure. This is the folder structure we use for Project Pegasus. In the Building a Collaborative Pipeline video series, I break down this folder structure and just to try to explain how we organized our files. I'm just going to copy the path to this directory and replace that. Need to make sure these is a / and hit apply. Houdini's loaded that package. So now if I drop down our file node, let's come inside, and I'm going to type in this custom variable, this Pegasus demo project. And that takes me straight to this path, which is our project folder structure. I'm also referencing this Pegasus demo project variable within this second variable, which is called Pegasus demo. So this will take us to the C drive Project Pegasus, the project folder structure, and then into a directory called Houdini Packages Pegasus Demo. So if I was to type Pegasus Demo, that takes me to my Pegasus Demo folder where I have all of the digital assets that we've been creating for Project Pegasus. So what we actually do is we can use this variable when we're saving our digital assets to ensure we save them into our project folder structure all together in this Pegasus demo folder. This Pegasus demo variable is also being referenced into this hpath variable, which is the Houdini path variable. And so when Houdini launches, it will search this path and load all of these digital assets that are stored in this OTLS folder. If I had a folder called desktops or toolbars, I could also save custom desktop layouts or shelf toolbar layouts for the whole team to use. And they could load these all using this package file. So now that I've updated this path, if I right click in Houdini, we could say I have all of the Pegasus digital assets loaded into Houdini. It also means users can use this path variable to reference files within that project folder structure. The custom variables are also important when using Houdini Engine in Unreal, as the package file is also loaded by Houdini Engine, meaning that we can use the path variables in digital assets and then use them in Unreal. In the Building a Collaborative Pipeline video series, I explain how to set up the package file from scratch to give you a full understanding of how to create the package files for your own projects. I also break down our project folder structure, showing you how we store our digital assets, source files, and Unreal project all within the same project folder structure. I also touch on using version control software and explain how to version digital assets. Version control software is a key part of game development, so I wanted to take the time to explain its use with Project Pegasus. Keeping all the digital assets and Unreal project files together in a single folder structure meant we could easily use version control software to collaborate and install a project on a remote server with a team committing and putting changes. I also show you how to version Houdini digital assets, allowing you to maintain multiple versions of digital assets and switch between them. I hope the Building a Collaborative Pipeline series helps demystify some of the kind of broader aspects of using Houdini and digital assets in your project. Next, I'm going to give an overview of the landscape creation. Here's the landscape that I created for Project Pegasus. I'll come inside. I'm just going to go through the this file, this digital asset. And this is the landscape that I built during the landscape creation video series. So it really starts with kind of a basic input shape for the island, just drawn out using some curves, which I've then poly extruded. And these kind of form the cliffs that run around the outside of the island. And then I have a series of just very basic primitives, some tubes, to create some mountains on the landscape. There, I've just got it all merged together. So then I can run this into a HIVE project, create the very basic shapes for the island. Obviously, this looks quite geometric, not very island-like at the moment. So I can add some noises. So first of all, I'm just creating a mask to mask out the area of the cliff. And that's just using a height field mask by object. Now I'm just going to blur, just shrink and blur that mask to give a nice fall off towards the edge of the island. And then I can start layering on height field noises to kind of create some interesting shapes. So here I'm just using a wally cellular noise just to add some kind of nice kind of cracks and lines that run across the landscape and just start to break up some of those basic shapes. And then a more subtle noise just to give a little bit more texture to the landscape. And then use a high field distort to really break up those shapes much further. And so now you can see I've kind of got a lot more interesting shapes, looks a bit more like an island. These look a bit more like mountains. And those lines we've got from the woolly noise kind of create these nice kind of fractures that run across the landscape. And what was those kind of very straight lines from the curve are now all nicely broken up. That forms the basic shape of the island, and I could then start layering on some erosion and different noises to start to build up the detail on the landscape. So here's the first Highfield Road. I only worked over a very small number of frames, so I'm only eroding over, or simulating over 5 frames. That was really just to bring down the time it took, the kind of simulation time, so I get a bit more of a faster feedback when I was adjusting these parameters. I actually kind of built this as a digital asset quite early on, so I could then bring this over to Unreal and work with Houdini Session Sync. So working over this small number of frames meant that I could kind of more iterate quickly backwards and forwards between Houdini and Unreal. Because I'm working over quite a few only a few number of frames, I've really ramped up the erodibility to kind of get some erosion quicker. Set this to 5 frames. Just see that erosion. Let's set that playback to 5 frames. there you can see we've kind of getting some erosion, some nice details added very quickly with a few number of frames. Starting to get some channels building up, some channels being carved into the landscape and some debris building up. So this is just going to create some nice interesting shapes kind of very quickly with these first sets of erosion. So I'm only working at a low resolution here, just 512 by 512. And then I could now on a different erosion node. So this time I've changed parameters a little bit. Still got quite a high erosion, but I really ramped up the removal rate for the hydro erosion. So this is starting to remove quite a bit of debris each frame of the simulation, and that results in these deeper channels forming on the landscape. Yeah, there you can see those kind of were very broad water river channels are now eroding down into the landscape, forming these really nice deep valleys. So then I start to increase the resolution a little bit. So I've just doubled it. So now we're at 1024 by 1024, so we're at 1K. Just adding a mask so that I can distort different areas of the map and add some kind of additional detail to the landscape. Now I've increased the erosion. And here I'm just using a height field remap to just adjust some of the height and shape of these mountains, kind of bring them up a little bit, give some steeper sides to get some more interesting kind of shapes. And again, layering on another height field road. Now we've increased that resolution. So I get kind of more detail in the landscapes, more finer channels appearing. So yeah, those channels will work. And previously quite low resolution, we start to see more detail appear in them. And they just started to erode a little further in these kind of finer areas. And I've increased the removal rate again just to remove some of that debris and help erode those channels, make them even deeper. And then again, resampling the node. This time we're at 2K. Again, just masking out some different areas, applying some more distortion just to add some very subtle detail. I mean, it looks subtle in Houdini, but when you think about the kind of size of this landscape compared to a person, these details are actually quite big. So at this high resolution, I'm just kind of working quite subtly. And then applying the last height field road. That just kind of gives some finer details to some of these smaller channels. And then I brought this digital asset into Unreal and kind of made some changes and previewed the asset, built a very basic material that uses these height field layers that we've got on the landscape from these height field road nodes. And here is that landscape in Unreal. So I can import it as a digital asset and then open this in Session Sync to kind of continue make changes and refine it. And I can easily hit play and just test out the landscape, see how it looks, check the scale, and make sure that I'm happy with everything that I can see. Also in the landscape video series, I go through an example file where I break down each parameter for the height field road node. So with this file that you'll be able to download with the project files, you'll be able to follow along where I break down and show how the different parameters kind of affect the erosion. And just break down each parameter one at a time and just explaining what each parameter does, its effect on the erosion. And I took the time to do this because I really found when I first started using the high field erosion tools, there's so many parameters and they have quite a bit of crossover between how they each parameter kind of affects the erosion, that I wanted to kind of explain each one so that when you come into creating the landscape, and I start talking through using these height filter road nodes, you have a much better idea of what parameters I'm changing and why I'm changing them to try and achieve the look that I want. Next, you'll hear from George on how he took this very basic landscape and turned it into the very detailed island that you see in Project Pegasus.
Hi, my name is George Hulm, and my primary responsibility on Project Pegasus was the landscape, which I took over from Ian after his initial setup. My responsibilities included setting up the pipeline between Houdini and Unreal Engine, detailing the terrain, texturing it, setting up paths on the terrain, scattering foliage, and doing sort of the technical setup inside of Unreal, such as specifying the settings of the terrain and setting up the landscape material. Now, when we set out to create the environment for Project Pegasus, we had a few requirements of the landscape. We wanted there to be a lot of variety. We wanted to reach a very high degree of visual fidelity, and we wanted the terrain to look good from all distances. In addition to that, we wanted to be able to support manual and procedural editing, have the workflow be non-destructive, and be able to support multiple collaborators. So essentially trying to replicate all of the constraints and requirements that we'll be seeing sort of in AAA development pipelines for creating open worlds. So to begin with, I'm going to focus in on these last three since they're sort of the driest part, and then we'll move on to the more pretty and interesting arty stuff. So to begin with, we're going to talk about the pipeline. We made use of world partition, edit layers inside of Unreal, and I'm going to talk to you as well about our caching practices and the way in which we supported a bi-directional workflow between Houdini and Unreal Engine, meaning having sort of changes in one environment reflected inside of the other one, which will allow multiple artists to work together to produce the end result. World partition is a feature of Unreal Engine 5 that automatically dices up and slices up the terrains that you import if you enable it. And it was really essential for creating sort of the giant open world terrain that we wanted to create. Additionally, it means that you have this feature toggled on called one file per actor, which makes it easier for multiple artists to collaborate inside of the Unreal Engine on the same map at the same time. World partition really just works. There's no need to do any specific kind of setup, although if you're working with Houdini, you do have attributes that you can set on your terrain geometry when you export it to disk, and then when you load it into Unreal, you're able to configure certain settings that relate to world partition. We didn't bother doing that, we just used the default settings. Edit layers are a feature of Unreal that allow you to basically have this layer stack where you have different height information contained within different layers, and you can choose how they're blended together and what order they get blended together in. And this is really great because this is what allows us to do the non-destructive editing of the terrain, where you maybe have your source ground truth terrain, and then you sort of blend in these different layers of detail without them sort of overwriting the contents of another layer. So again, this is great for non-destructive workflow and for collaboration. So we made use of this feature. And again, Houdini has great support for this out of the box. So you have attributes that you can set on your terrain geometry when you export it to disk. And then when it gets loaded into Unreal, if you have these attributes set, you'll be able to decide which layer you want to update on the terrain or read from. So this just works really well. It's very seamless and it's very, very quick as well. All right. So now the probably most boring part for most of you, they're going to talk about the caching practices and how we got this kind of bi-directional workflow going. So essentially what I mean by caching practices is we didn't want to just work with Houdini Engine inside of Unreal. We wanted to be able to work both in the Houdini environment and inside of Unreal, so sort of independently of each other and benefit really from the strengths of both programs fully. So the way in which we did this is we set up an external cache on disk, and you can see that we have these three files here, the source, manual, and procedural detail. And basically each of these represents one of those edit layers inside of Unreal. And when we have a change made inside of one of those programs, we'll export it to disk, and then we'll be able to see it inside of the other one. So we built some digital assets to help with that. We've got the load landscape digital asset and the cache landscape digital asset, so they should be fairly self-explanatory. These run inside of the Houdini environment, and they also run inside of Unreal as Houdini digital assets, where you have a variety of settings relating to which layers you want to load or save to disk. So this was really very simple and a very quick way of kind of working. And it meant that we had one source of ground truth that always lived on disk that multiple artists could reference and read from. So that's basically what this diagram is trying to explain or visualize. And you can see that we've got that on-disk cache there, and those 3 files, source, manual edits, and procedural detail. And this diagram is basically just trying to show the flow of information. So we have our incoming height field, which was our starting point, and then that goes for a procedural detailing phase and into Unreal. And any manual edits we make inside of Unreal go back to the Houdini environment so that the procedural detail can then be aware of it. And it's sort of this iterative feedback loop that ensures you've always got the latest state in both programs. So that's how we sort of supported multiple users and also, having that kind of non-destructive workflow and having that bidirectional relationship. So that was all the dry stuff out of the way. Now we can talk about the sort of fun, pretty, arty stuff. And I'm going to start off by talking a little bit about the materials workflow that we built for Project Pegasus. And this is sort of really how we detailed and textured the terrain to sort of a higher degree of fidelity, as well as the authoring of these global color maps. So materials workflow, I'm not talking about Unreal materials, although we will get to that in a bit. I'm actually talking about the use of materials directly inside of Houdini to add detail and color to the terrain. So we made use of scan-based detail to take the terrain that we see on the left here, and sort of using masks inside of Houdini, we were able to decide where to apply the detail from various different scans to add this extra layer of fidelity. And just a little bit of by way of explanation here, we obviously have really great tools for sort of sculpting those larger features and forms on the terrain, the erosion, simulating sand fall, deposit, sediment transfer, and all of that kind of thing. But what a lot of terrain tools actually really lack is the kind of tools that allow you to sort of work in extra details on the more sort of micro level. So that's why we took advantage of scans, because you're really able to inject an extra level of a really rich detail in that kind of sub 10 meters level of terrain scale, which we felt really added a lot more on top. And we did this with our custom-built Pegasus height field material node. And what the Pegasus height field material node allows you to do is to take a mask. So you mask a certain feature of the terrain, maybe the slopes, and then essentially you set up this height field material with all of the channels of a material, maybe from Megascans, maybe from somewhere else. And so basically we have this holistic material development process, much like you'd find in a tool like Substance Designer, where you're able to sort of update the color and the roughness and the height simultaneously, just as if it was a material, but in the context of landscapes. So then we basically repeat this process. We stack loads of these nodes together, each with their own masks coming in from outside somewhere. And we're able to decide where we want the grass materials to get placed, where we want the cliffs, the gravel, the sand, the paths. And all of these materials are being blended together to modify not just the color, to author the global color texture that we see there, but also to sort of displace it and add that rich topological detail that I mentioned previously. And here you can see the actual graph that if you decide to follow along with the sort of multi-part series that I've been developing for Project Pegasus, showing you how we built the terrain. This is the actual graph that we're going to build together, and you can see how those layers get blended together to produce the final result. So yeah, that's what that looks like. And here it is running inside of Unreal with the material. So we'll get to this a little bit later on. The height field material node is just one node in a suite of tools that allow you to sort of manipulate and edit the color of the terrain. So we've also built a couple of basic tint functions, power operations, change the ability to change the color space and remap and blur the color. So this is a kind of growing library of nodes that you can think of as basic image manipulation functions that works directly on height fields. So it's quite a nice toolkit, and I definitely enjoyed working with it. I'm excited to see other people maybe sort of using these tools and seeing what they come up with. Okay, so we've talked about the global colors and the materials workflow, and really the goal with all of this toolkit here was to make sure that the terrain works at all distances. So we're not just relying on detailed textures up close, but we're also authoring a global color map. We don't just have large scale terrain features, but we also have some smaller, closer up ones. So that was really built to sort of try and get to this goal, though of course getting high visual fidelity and variety was also a part of that. In addition, to really push that level of visual fidelity and variety a bit further, I'm going to talk to you a little bit about the kind of workflow that we used to add the tiling details, the tiling materials to our terrain. And the way that we did this was through the use of an ID map, which we used instead of weight maps. So first of all, I'm going to talk to you a little bit about how traditionally we handle landscape materials inside of Unreal. Traditionally, if you want to assign a material to a portion of the terrain in Unreal Engine, then you'll create a weight map, which is a grayscale image which defines the strength of one material in a particular location on the landscape. And you'll use a bunch of these to define the distribution of the different materials across your terrain. So an ID map, essentially, what we're trying to do here is instead of having one grayscale image per layer, we just have one single grayscale image that defines the distribution of all of the layers across the terrain. And you can see here that in Unreal, we're just sort of visualizing each of those different layers contained in the ID map as a different color on the landscape. And here, if we've sort of zoomed into the terrain, you can see the individual values or the indices that are being extracted from that ID map. So we've got a region that has a value of 1, value of 5, and a value of 4. And we can use these indices to essentially assign a different material to a different part of the terrain. And this is really how we approach trying to add a lot of variety to our terrain. Why couldn't we just use weight maps? Well, I'll talk about that now. So when you want to have a high degree of variety, then that means you want to have a lot of layers that you're able to support on the terrain. So, it's not enough just to have grass and stone and gravel and, 3 or 4 different layers. You really want to be having like 10, 15, maybe even 20 or more individual materials that you're able to apply to your terrain. And the problem with weight maps is that this means that you're going to need to have a grayscale image that defines the distribution of each of those individual 20 layers. So you have one weight map per layer. With Pegasus, with the ID map, we just have one ID map total, regardless of the layer count. So essentially, we're able to avoid having a memory cost that's tied to the number of layers. We just have a fixed memory cost with that one ID map. And additionally, we also don't have to worry about sending backwards and forwards between Houdini and Unreal. All of these individual weight maps, we just send backwards and forwards one. Now, what's the downside of this approach? Well, if we zoom in really close, you can maybe guess, and that is that we have really harshly defined boundaries between the different layers. They're all just solid values in the pixels. There's no blending. And what that would look like if we naively applied it to the terrain and just used the raw indices is something like this, where you can see a very clear pixelated pattern. And in a little bit, I'm going to talk about the techniques that we use to avoid our terrains looking like this and looking a little bit more like this. But before we get to that, I'm just going to talk about the tools that allowed us to develop this ID map inside of Houdini. And it's quite simple. We define sort of a set of layers. So we're instructing Houdini what the different IDs in our ID map relate to. So this is just really helping us to set up a nice user experience where you name your layer and you give it a color. You can work interactively in the viewport. And then you use a mask. You tell the ID map which layer you want to inject into it and which mask you're going to use. And then that sort of injects that information to one of those ID maps. And we also have the ability to extract sort of a mask from the ID. So you can say, okay, I want to see what the contents of the grass 2 ID looks like. And then you've got this mask back out of it. So you can see that really they're just masks, but they're all contained within a single image. And then the workflow is after you've set up the layers that you want using the ID map layers node, you basically string together a bunch of height field layers to ID nodes, and that allows you to fill out the different values of the ID map. You can see that every layer is essentially its own sort of grayscale value there contained within the ID map. So we're just reusing the masks that we created during the height field materials tooling process. So it's sort of really nice toolkit that all works together to allow you to sort of embrace this new workflow inside of Houdini and Unreal for texturing terrains. So I mentioned before that we had to come up with some sort of tools or techniques inside of Unreal to be able to read the ID map and to get it to look a little bit better. So I'm going to start talking to you about the material. And I'm also going to talk to you a little bit about texture arrays. So the traditional paradigm inside of Unreal is that you have a bunch of weight maps and then you have sort of a material definition. So in this case, we've got our grass layer. You sample the weight map for the grass layer, and then you maybe sample sort of all the textures for the rock layer, and then you have the weight map for that, and you blend all of these different layers together, and you can think of each individual layer as a whole material in of itself. So this is also problematic from the perspective of memory and shader complexity, because not only do you have sort of n weight maps, that is weight maps times the number of layers, you also have number of texture samples times the number of layers. And since you tend to use more than one texture to define a material, you have the color, the normal, and then maybe some masks, you're going to end up with this sort of multiplying together to further increase the amount of memory that's being used, but also just increasing the shader complexity sort of linearly as you increase the number of layers. And this is again sort of a limiting factor that you have when you're working with traditional Unreal landscapes. So this would have really prevented us from getting that sort of higher degree of variety that we wanted to be able to achieve. So we used a new feature, or a newish feature inside of Unreal Engine, which is texture arrays. And what texture arrays are, they're sort of a vehicle that allow you to sort of plug in a whole set of textures into one asset, and then you can sample that texture array inside of the material. And by providing the texture array with an index, you're able to sort of apply the textures that are contained within that index to that portion of the terrain. So you can see here we've got this sort of drop down with a bunch of indices, and for each index of the array, we're adding a new tiling texture. And of course, I've used the word index a bunch of times now. So we're just feeding into this texture array the indices that we get from our ID map. And that's what we can see here. Every color is its own ID. And then we're extracting from that texture array a different tiling texture according to which ID is currently on that part of the landscape. Now, I also mentioned previously, and it's quite clear to see in that last image, that if you just do that naively, you get this kind of sort of bit-like appearance where you can clearly see the pixels. And the way we get around that is we just sample the texture array 4 times with a slightly offset sample from the ID map. So sort of you can imagine this as for every pixel on the terrain, we're getting the top, left, right, and bottom sort of value from the ID map. And then we're going to just blend all 4 of those samples to produce the final result. And that gives you a smoothly interpolated material on your terrain that looks just like this. So that's how we get around that. And what we get as a sort of a benefit from that is, whereas before we have an increasing number of sort of weight maps, we have an increasing number of texture samples and an increasing number of amount of shader complexity. With the Pegasus material, you have just one ID map. You have maybe, let's say you're using color, normal, and masks as your textures. You sample each one 4 times. You have just a total of 12 texture samples, regardless of the layer count. And you also have that fixed shader instruction count, which doesn't increase as you increase the number of layers. So all around, this approach is much better when you're trying to deal with extremely sort of large open worlds and you want to be able to support a high amount of variety there. Okay, so onto the kind of more detailing of the terrain, the more arty stuff again, after we took a bit of a detour into the sort of technical territory a bit. So this is basically how we approached creating sort of paths, tracks, and trails across our terrain. We built a node called height field paths, and the height field paths node takes in a height field as an input, some waypoints, and then it will create some paths across the terrain. Inside of the height field paths node, you have some settings, and these are essentially the costs of traversing different regions of the terrain. And by default, there's going to be a cost associated with sort of going uphill. That's what this rate of change of height cost is here. And that's the kind of cost that causes paths to sort of wiggle up slopes. Then you don't really want paths to be able to traverse the steepest cliffs. So we just have a raw cost associated with traversing slopes of varying steepness levels. And then that would just kind of be basic. So to take it one step further, we also have the ability to blend in any other kind of masks we want. So in this case, I'm using the occlusion of the terrain, which really picks out sort of the ridges or the valleys and causes the paths to prefer to move either along the ridge lines or in the sort of the gullies and furrows of the terrain. So you can see we've got this visualized here with 3 different colors. These sort of green paths prefer moving along the sort of ridge lines and more exposed areas, whereas the red ones are sort of moving through those valleys and furrows a little bit more. So you can really try to sort of art direct and describe the behavior of whatever creatures have been leaving these paths across the terrain. We also, of course, have the ability to sort of set waypoints. So here you can see there's a waypoint on top of the mountain, and then with the costs that we've created inside of the height field paths node, we're able to define the kind of behavior of that path as it sort of creeps up the terrain. And here again is another example of that. And here's the same thing, but with just a few more paths. So you can see how you get really interesting looking paths across the terrain with some very simple controls there. And the benefit of this is that we're able to sort of add a lot of interesting sculpted detail to the terrain that it would be really hard to either add this manually or to sort of manually draw these lines. And there's no sort of simulation process that will do this for you. So the height field paths node really allows you to create this extra layer of detail, and not just for the sort of main paths that the humans are using, but also sort of to describe things like animal trails, which can then be used to change what vegetation would spawn, how bare the tracks are and how short the grass is, etc. So we take that through into the color layer, we take that through into the ID map, send it all over to Unreal, set up a new set of textures in the texture array, and then we have the paths described and represented inside of Unreal there, adding a lot of visual interest to the terrain. And this was really helping to help us push the high visual fidelity. So some other things that we did was, of course, adding props to the terrain. So the distribution of trees and woodlands. The way we did this, it was really fairly straightforward. We just masked certain regions of the terrain. We scattered some points in them. And then to take it one step further, we created this node called height field advect points. And the most simple way of thinking of this is it allows you to roll points up or down the terrain. So this is what the flow map looks like if you roll those points up and leave a trail behind them. And this is what it looks like if you roll them down. You could imagine that if you roll them up, you're going to sort of get the rocky ridges. And if you roll them down, you're going to sort of get the scree and boulders that have fallen down the hill. And in the context of vegetation, what can be really interesting is to actually, instead of using the slope, you use, again, the occlusion. So you can roll points towards or away from occluded areas, which sort of simulates or emulates the way in which different types of vegetation might have a preference for different levels of exposure or different levels of moisture in the soil. So this is a really nice and interactive way to sort of art direct those points after the fact. And here you can see that we've just imported those points into Houdini using a raw kind of import tool that Houdini ships with. And you just provide a reference to the asset that you want to scatter, and it just spawns it straight there. You know, there's no heavy information or data being sent from one program to the other. This is pretty much instantaneous. You drag in the scatter and it's populated with the trees. So really great work by the Houdini engine team to get that working as well as it does. And now I'm going to talk a little bit about the scattering of the smaller foliage and vegetation, because we don't want to be sending the millions and millions of points from Houdini to Unreal that would describe every blade of grass, of course. And to do that, we just used the native landscape grass system. Inside of our material, we have the ability to define which grass type we want to associate with which material layer. And those grass types are defined by grass type assets. And you just read that into the master material, masking out the different IDs of the ID map. So basically working in a very similar way to the way that we sort of sample the texture array and grab a specific index from there. In this case, we're just grabbing the index of the grass type that we want to assign to a different region of the terrain. To add new grass types, it's as simple as going back into Houdini, creating some new masks, maybe sort of modulating the global color and ID map, and then bringing those back into Unreal and setting up that new grass type selection there. All right, and finally, and possibly one of the more exciting things for a few people, I'm going to talk a little bit about nanite terrains and displacement and tessellation, which are all new features, somewhat experimental in Unreal 5.3. And I can definitely say, despite the experimental nature of these tools, they work very well out of the box. You may be able to see a slight seam along the terrain there. We did actually end up fixing that quite simply. So if you follow my sort of mainline tutorial series on setting up this terrain, then I'll discuss the ways that I address that. But you can see just how much detail gets added to the terrain through this runtime tessellation and displacement feature. In order to get this working, you just need to turn on Nanite on your terrain by toggling a switch and hitting build data, and also going to the default engine .ini file in your project location and adding these two lines to allow tessellation as a feature. And I'm sure that we'll be seeing this becoming more of a first party or more of a well-supported feature in the future. So that's just the setup inside of Unreal there. And now I'm going to basically show you what it looked like previously to turning on the displacement. You can see it sort of looks quite last gen, a little bit low res. And then if we just fade in the tessellation there, it makes a huge difference. So can't overstate how great it is to have this feature back inside of Unreal Engine. Of course, this doesn't come for free, and we noticed a pretty sizable performance cost from turning this back on. But that being said, I think that the cost in this case was benefit, since we're making a kind of showcase project and we want things to look as good as possible. So yeah, that's the difference there from left to right. That's the end of my talk. At least for now, I'll be back a little bit later to talk about the Flora tools that we've been prototyping, which I'm really excited to share with you. And you've got a ton of other interesting stuff coming up from the other artists later on in this presentation. So thanks for watching, and you'll hear from me again later. Bye for now.
Building on top of the pipeline that George created, I'm next going to demonstrate how I generated the procedural cliffs for Project Pegasus. We really wanted to push for a high level of detail in Pegasus, particularly in the landscape, and demonstrate how Houdini can be used to create procedural art that utilizes Nanite. Producing the cliffs presented a significant challenge. The workflow uses several digital assets assembled into a TOPS network, which take the island, convert the cliff areas into geometry, and then split them up into separate work items. Then each individual cliff is subdivided, displaced using height maps, and split into smaller tiles. These smaller tiles are then imported into Unreal. With a single cliff being up to 7 million polygons, importing that amount of data became a real challenge. Nanite was really amazing at displaying all that geometry in Unreal, but it was the import process that was the challenge. This is by no means a quick process, it takes patience. Working in a larger studio, you may have access to a render farm and can distribute work items to several machines to speed up the cooking process. But for myself, working on a single machine, as I imagine most of you are, it took a few hours to cook the cliffs for the entire landscape. It then took several more hours to import that geometry into Unreal. Houdini and the TOPS network largely automate the process, but of course the process still takes time. I didn't want to shy away from demonstrating the full workflow, even if that meant crashing Unreal and going through the process of troubleshooting and showing you how I got around some of the memory issues when importing that amount of geometry into Unreal. The amount of detail that can be rendered in Unreal using Nanite is truly amazing, and so I wanted to take the time to show you how I achieved the full final result. I'm just give a quick walkthrough of the workflow. So to begin with here, I have several different digital assets. The first one is a digital asset that George developed. This loads the separate layers for the landscape and assembles them into a single height field. On the landscape are different ID layers. We have one for the cliffs, which I can then use to extract the cliffs from the landscape and convert them to geometry. With this digital asset, I can adjust this delete small cliffs threshold. So if I increase it, I just get the largest cliff sections, or I can reduce it if I want to include some of these smaller sections. If I just separate out a single cliff, and then we can see that cliff subdivided and displaced using height maps. I'm subdividing the geometry quite heavily and using height maps from the Quixel Megascans library. Just come inside and I can go through the process. So we're subdividing the geometry. Just temporarily disable that. And I'm using the labs triplanar displacement node to displace the geometry. I'm actually displacing 2 copies of the cliffs with 2 different height maps. And then blending that together with a mask. So this is the areas that are being masked, and we're blending it between the 2 different displacement maps. So this adds more variety to the cliffs and also hides any obvious tiling. The height maps have some really nice details, such as these overhangs. But when we view this on the landscape as a whole, we can really clearly see these very straight lines running across the entire landscape. So to tackle this, what I actually do is, after I've subdivided it and before I displace it, I displace the geometry in the Y direction using a noise. If I reduce this element size a little bit, and that's just subtly warping the geometry. So I can then apply the displacement, blend them together, and now restore that Y position from before it was displaced. And that results in this warping on the tiling textures. If I just restore that element size back to 500, make it a little bit more subtle. So you can just see that subtly warps these lines. This gives a bit more of a natural feel to the cliffs. So that keeps the displacement in the X and the Z axis, but just restores the Y position of the points before I distorted it with this noise. And then I have a poly reduce just to reduce the poly count a little bit and optimize the geometry, because we do have some smooth areas where the poly count isn't needed. This particular cliff is around almost 2 million polygons, so you can just see how much detail we're able to get into these cliffs and able to import into Unreal using Nanite. Because I have that geometry to work with, I can also generate some masks to store as vertex color, which I can then use with material to add even more detail. So I have the lamp's curvature node, which I'm using to generate a convexity and concavity mask. And then I'm also generating an ambient occlusion mask, which I can store in the blue channel. Then I have at the end here a final digital asset, which takes these larger cliff sections and splits them into separate tiles for importing into Unreal. I then take these digital assets and assemble them into a TOPS network. In here, I have HDA processors which load those digital assets into the TOPS network. So first of all, I'm loading the landscape, extracting the cliffs from the landscape, and then I'm able to split those separate cliffs into separate work items. So if I just generate this node, we can see all of those cliffs loaded as separate work items. So you have total generated 298 different cliffs, which I'm then able to process. I'll generate the high poly geometry for each one of the cliffs, split them up into tiles, and then save those tiles for importing into Unreal. Once those are split up, I end up with between 400 and 500 separate files to import into Unreal. And to manage that process, I create this file pattern digital asset. This simply allows me to use file pattern string to load the different files into Unreal in smaller batches, and this helps me avoid running out of memory when importing so many large files into Unreal. And here are the final results in Unreal. So with the combination of the Nanite geometry and the Unreal material, we really get a lot of detail in these cliffs. And let's just visualize that Nanite geometry. So here you can see all of the Nanite rocks and outcrops, as well as the Nanite trees, and then all of the detail in the cliffs. And if I just select all those cliffs, so here you can see just how much geometry has been generated by the TOPS network. I really hope you enjoyed this video series, and you really see the power of using TOPS to generate large amounts of procedural geometry. So that covers some of the workflows for the landscape and environment art that we created for Project Pegasus. And next we move on to talking about a tool that I created to pile up objects and create piles of debris. The tool works by scattering points on a grid and then copying the input geometry to the points, and then runs the objects through a rigid body bullet solver to pile up the objects. For this tool, I exposed the gizmo for the grid that's inside the digital asset, which I can use to manipulate the shape and size of the pile. So as I begin to rotate the grid, the tile begins to tilt and objects fall off. I've created options to change the density of the pile, as well as an option to randomly rotate the objects, which can be used to create more messy piles of debris. To keep the objects in a uniform pile, the geometry is dropped into a container. There's also an option to disable this container if you want the objects to be scattered further. At its core, the tool is relatively simple, just running objects through a bullet solver, but I wanted this to be a robust tool that could be used in a variety of ways, in particularly showing how to create an option that allowed a user to specify how they wanted to split the geometry and show the logic behind it. For example here, I have some objects which I've imported from the Megascans library, and I've merged them all together so they're now one object. So the first option is to split by connectivity. This assigns a unique integer ID to each of the connected pieces of geometry. The tool could then split that geometry up and copy these individual objects to the points. And now if I increase the frame number, we get a pile of objects. In this example, I have a single object. These are pieces of firewood bound together by rope. But when splitting by connectivity, all of these individual pieces get split up, which is obviously not what I wanted. So the second option is to specify a piece attribute. So here I have a name node where I'm creating a piece attribute called name and giving it a unique name. So in this particular case, I'm calling it firewood. So now I can switch to the option to split by piece attribute, and I have the geometry scattered to the grid as I'd intended. And with this particular option, I wanted the user to be able to specify the piece attribute they wish to use. So I go through the process of explaining how to build logic that allows a user to specify their own piece attribute. I also include functionality so that a user can input collision geometry so that the bullet solver simulation can interact with other objects. Lastly, there's an option for Unreal instances. So with this option, the digital asset outputs points with transform information and an Unreal instance attribute. When using Unreal, rather than outputting new geometry when baked, Houdini Engine can instance the inputted static meshes to the points. So with this video series, I demonstrate how to build this useful tool, as well as to create logic that can make tools robust and flexible. Next, I'm going to demonstrate a workflow for using tops to generate procedural assets. In this video series, we take a very basic input mesh, generate a high poly procedural model, create a color ID that we can use to blend together different materials in Unreal, as well as creating a detail mask with convexity, concavity, and ambient occlusion masks. With the input mesh, I create a ID for the different materials. So we have the main stone area of this headstone, and then a metal plate in the center. The procedural detail is created by increasing the resolution using a remesh grid, and then using various noises to add additional detail. So I'm using attribute noise and the side effects labs edge damage node to create some detail on the stone. And then I also use some attribute noises and masks to create some moss growing on the surface of the stone. Again, for the metal, we're using a remesh grid to increase the resolution, using some different noises to create a kind of hammered metal look. Also using a mesh sharpen to give it a bit more of a stylized look. And then for each area we have a color ID, so the moss is kept black, the stone is red, and then the metal area is blue. And then I can use these IDs in Unreal to blend together the different material on the different areas. And then doing some optimization and reducing the poly count a little bit, just to optimize the geometry before I export the file to disk. Because I have two different IDs, I wanted to bake the maps to a texture rather than bring them in as vertex color. I found a very quick way to generate UVs was to use the connectivity and segmentation node. The connectivity and segmentation node splits the geometry up into different segments, and then these different segments could be flattened into UV islands. I found this a very fast method of creating UVs on high poly objects, especially when compared to something like the lab's auto UVer, which works great on low poly objects, but can be very slow when we've got lots of geometry to work with. So I found this to be a very quick solution. I'm saving those two masks as texture maps and exporting the FBX to import into Unreal. And here I'm using the lab's measure curvature node and the mask by feature to generate the convexity, concavity, and ambient occlusion masks. Because I'm not baking from high to low poly, I use a COPS network to import the color attribute and save it to a map. This workflow then demonstrates how you can have multiple objects run through the same network using tops. At the beginning of the workflow, there is a small amount of manual setup where we set up the base meshes with the attribute that defines which areas are stone, which areas are metal. We then build this tops network, which loads each of the base meshes, processes them to generate the high poly model, and saves each of the masks and FBX files to disk to be imported into Unreal. If I just select one of these work items, I can show each of the high poly models that are generated by this tops network. So the aim of this workflow was to build a procedural network and then demonstrate how you can use tops to automate the process of running different input meshes through that procedural network. I then go through the process of importing those files into Unreal and building the material. Next, you're going to hear from Feike, and he's going to talk about how he created the buildings for Project Pegasus.
My name is Feike Postmes. I've been also responsible for the architecture of Project Pegasus. A little overview, I'm going to go over the input of what shapes we've been using. We've been using some PCG to do some terrain sampling and data tables. Help you guys dealing with large amount of data. So the reason why what I wanted to focus on for this project was mainly on how to do a nice workflow together with other people, and a workflow where you have lots and lots of data. Because sometimes, depending on your project, it can be a little bit difficult to be working with Houdini Engine. It can be insanely powerful, but it can also be sometimes a little bit unintuitive or difficult. And I want to go over different methods to help you guys shape up that pipeline to make it a little bit easier to deal with that high amount of data, especially when it comes to transferring data from Unreal to Houdini and back again, to make that go a little bit smoother. So what I did, and this is actually something I don't always recommend, I made HDAs which are the shapes of our building system. It has its pros and its cons. Its pros are mainly that you have a lot of control regarding what you want these shapes to be, if you want to give them custom attributes, if you want them to be customizable in a certain way. But it has the downside that it creates a lot of clutter, especially when working with Houdini Engine. It doesn't like, it becomes a little bit less stable when you use a lot of different HDAs which are connected to each other. So it's possible, but definitely try it out first with a very, very saturated setting where you use a lot of your HDAs before you hand it over, just to make sure it all works. Otherwise, you can always just use regular shapes and make sure that's only one input for your HDA, which makes it a lot more stable. Then we are going over a PCG setup, which is the terrain sampler, which helps you with the power of PCG to basically sample the terrain. Because right now, if you would throw the entire terrain into your asset, that can be very, very time consuming. Definitely if you're not working on the most high-end PC. And it's also just not needed, because usually you don't need that much of the terrain for your building. You just kind of want the area where the building is. And this makes it a lot easier, because then you're using the internal tools of Unreal to do this terrain sampling, which helps a lot because you're not sending over the entire terrain. And finally, over here we have the data tables, and I'm going over some generation methods in Houdini, and also to actually use those generation methods to generate these data tables. So we generate a bunch of different assets in Houdini, and then we load them in immediately into a data table. And this data table is then being used to give this information back to your HDAs. So you're not giving 20 different stones, manually selecting them and adding them to your HDA. That can also be very time consuming, and especially it can go wrong if you have multiple artists working with your tools. And it's a lot easier to just give them a data table and be like, load in this data table. It has the bounding boxes, use it for your placement. And this can definitely be a great workflow improvement. So we'll be going over this as well. That's a little bit of a recap of what I'm mainly focusing on for the buildings. We are not focusing that much on awesome placement techniques because, well, first of all, there are already an insane amount of cool tutorials regarding cool placement techniques. And there was only so much time. So this is the main focus we've had. I hope you will enjoy the videos.
Moving on, Alex is going to talk about how he created the amazing clouds for Project Pegasus.
Hi, I'm Alex Hamer. I'm a technical artist and I recently graduated from a master's in game development from the University of Gloucestershire. This project has essentially been my first step into the industry, and I've been super thankful and excited to be working on it. The goal was to give artists options to create AAA quality cloudscapes in Unreal Engine without the use of third-party plugins. When I joined the project, about a few months in, the environment was starting to move on from the blockout stage and was using a community cloud plugin for its clouds. We needed to replace this system entirely. The ultimate dream for what I wanted to achieve was to create a system where artists could create high-quality clouds in Houdini and have them directly implemented into the volumetric cloud system in Unreal Engine as transformable objects. This would allow artists to make last-minute changes or drastic changes in-engine. For example, if a cloud was scaled too large, positioned in the wrong way, or even the density being too strong or too sparse, instead of having to re-export and make changes from Houdini, they would be able to adjust all of this in-engine. This is an undeniably more efficient workflow, as opposed to having to switch back and forth between software and waiting for rendering or baking. You may be wondering why we chose to go with extending the default volumetric cloud component instead of creating an alternate system. Well, this is majorly because the volumetric cloud component has come with every release of Unreal Engine since 4.26, and extending this would be the simplest solution and wouldn't require an advanced knowledge from the end user of how volumetrics work in Unreal. Just as a reminder, we are still targeting solo or new artists just as much as we are more experienced teams of artists. To start out, I'd like to describe the state of the capabilities at the time of the beginning of the project. Unreal Engine version 5.2 had recently been released and there was no native VDB support. If you're unaware, VDBs are a standard for storing volumetric data and allow extremely high quality volumetric data such as clouds, fire, smoke to be packed into a file format which can be recognized amongst software. There was plugins that were created by third parties which added native VDB support to Unreal Engine, but with the limitation of the project being no third-party plugins, this could not be used. Thus, how would we get things to be drawn into the volumetric cloud material and updated in real time, or as close to real time as possible? Well, I was left with very few options, but render targets seemed to be the obvious solution. I went through a few initial ideas of how to utilize render targets in the most efficient way, but to also allow the highest quality possible, and a one-to-one transition of data from Houdini to Unreal. Drawing render targets into the volumetric cloud system did already exist, and a tool came with the volumetrics plugin if you enable it. It's still there. In this tool, you can essentially paint the clouds to a single volumetric cloud layer. However, this is only at one single height, and only has one noise type, so there is a very limited customization. This may be relevant to know as well, but within a level in Unreal Engine you can only have one volumetric cloud component, so you can't just create multiple layers and have them at different heights. There is only one allowed within the world. After going through a few iterations, eventually I reached a point where I decided on a method where we would split up the cloud layer vertically into tiles. So on a grid of 256 tiles, the first grid would be the bottom altitude and the final tile would be the top altitude. The plan was to designate an XY area, and then each cloud would be an actor that could be dropped into the world within this space and would create and update its own dynamic material instance in real time of where it was within the XY area, which it would send to the main blueprint. Here you can see this updating in real time. This main blueprint would then map it vertically to where it was between the bottom altitude and the top altitude and apply it to the render target in the correct tile space. Then, within the material, this render target would be read as a pseudo volume texture. If you're unaware, volume textures are a unique type of texture which stores 3D information as 2D textures. In Unreal Engine's own words, they work by slicing up a 3D shape into cross sections and placing them into a 2D grid. This should sound familiar to what the plan was here with the tiling system, and I hope you can see already how these link together. Here you can see how this looks when I move things around in the designated XYZ space, which can be set obviously in the main blueprint. You can see how it is being updated on the cloud actor's dynamic material instance, and how it looks on the final render target when we move it up, down, and left and right. So, using a couple of material functions, we can feed the render target into a modified version of the default volumetric material, and we can see our result being updated in real time. Though we are still missing a key feature. How would we get the cloud shape data from Houdini into Unreal and into this system? Well, we would use volume textures again. We can use the lab's volume texture export node and export the cloud that we have in Houdini into slices, which can then be drawn vertically and horizontally onto the tiles within the render target. And this produces a shape in resemblance to our original cloud shape. This also, though, allows for transformation, scaling, and rotation in real time. There was a lot of blueprint and mathematics and calculation work behind this, and I hope to release a video in the future covering this in further detail. Just to recap, if you imagine a volume texture with our cloud has 16 tiles, we draw the first 8 tiles into the tile space up to where we are in the world space vertically, and then we draw the remaining 8 after. This also allowed for scaling as well, where you would draw 2 of the same frame and have things scale along the vertical axis. The XY scale of the clouds could also be changed relatively easily and quickly within the dynamic material instance of the cloud actor itself, by simply stretching the texture sample. Another thing I'd like to mention is that it is possible to convert render targets into actual volume textures in Blueprint, which you would have thought would have made this process simpler. However, this conversion is not meant for real-time use like drawing to render targets is, and it would have frequently caused crashes. Therefore, creating fake volume textures worked just as well. So now we had a system where we could get clouds from Houdini into Unreal and move them around in real time, allowing true 3D cloudscaping. This obviously still had some issues to sort out, such as the voxelization level and the blending in between the different layers. As if you think about when we slice up our cloud shape, we lose the data between the slices. But an event that happened around this time caused the system to be discontinued in favor of another system. This event was the beta of Unreal Engine version 5.3 being released to the public, which notably introduced native VDB support to Unreal Engine. This was a huge deal, as it allowed extremely high detailed volumetric effects to be rendered in programs like Houdini and taken into Unreal without the trouble of third-party plugins or extensions. So, seeing the capabilities and what was now possible, I decided that it would be a mistake not to explore this new utility. Thus, from what I'd learned previously with how the volumetric cloud component worked from developing the previous system, it was fairly easy to set up some basic blueprint and material logic to have VDBs move as transformable objects within the scene. A quick shout out to Thibault Lambert for the original material logic with the matrix transformation. He beat me to the punch and released a demo only a couple of days after the beta's release. However, with my system, I wanted to give as much control to the end user, but also to not overcomplicate things. So I chose to have the traditional transform controls, as well as a uniform transform and a density multiplier, as well as some quality of life controls such as quick enabling and disabling, as well as labeling, as it could quickly get quite overwhelming scrolling through an array of many different controls and settings. Within this system, we essentially calculate the world coordinates of the volume texture in our world space. We then lerp all of these clouds into one final combination and feed it into the extinction. The result of this work is an array where we can quickly click add, input our VDB file, set a label, and set up the transform, and play with loads of controls very quickly, and adjust lots of different variables about how our cloud appears in the environment very quickly. With some tweaking, this system is the final system that we decided to go with, and enabled AAA quality VDBs to be utilized directly from Houdini without losing any detail or information, for example via volume textures, where the space between the slices would be lost data. Unfortunately, this system still had a few limitations, as it is still new technology. In Unreal, within the material editor, usually when you're working with multiple or many texture samples, you can increase past the default limit of 18, I believe, by changing the sampler source to shared. However, with sparse volume texture samples, this is just not possible. So a maximum of 6 VDBs is the highest number of clouds possible with the material. This, however, didn't limit the project, as the Skybox node allowed massive sky layers to be in one VDB file, which was extremely useful. It was around this time where I gained access to the Houdini 20 beta, in which I was able to utilize next generation cloud utilities. This involved the previously mentioned Skybox node, which allowed me to create an entire cloud layer in one VDB, or utilities allowing me to turn polygon meshes specifically designed around the environment into cloud primitives, which I could then apply some secondary procedurally generated shapes to, and brand new noises such as billowy and wispy noise to create the final result of cloud types such as cumulus clouds being shaped around the mountains. So I set out on creating a cloudscape using all of the new tools that were available to me. Referencing some of the blockout models created by Ian, the lead on the project, I then used all of the new cloud utilities, specifically the billowy cloud noise node, which generates that swelling, puffy look typical of cumulus clouds, to create some clouds which were tall, billowy, swelling towers forming around the taller mountains within the environment. These look great, and I had some large cumulus clouds in my scene. However, this still felt bare and empty. Within the blockout, there were also some higher level lighter clouds, which resembled cirrus clouds, which is another extremely common type of cloud formation. Cirrus clouds don't really have a particular shape and are instead more of a flat layer made out of channels of wispy noise. So I chose specifically to use the new Skybox node with the inbuilt noise functions to cover the entire terrain with a wispy cirrus cloud layer. The main reason that I did this is because trying to generate that flat layer shape with the generation tools would have been more challenging, and I found it easier to produce results which I could then mass adjust with the Skybox node. As well as this, the blockout nodes look good for a representation of cirrus clouds. However, again, they wouldn't be particularly useful when trying to create the initial cloud shape, which we would then apply the noise types to. These also look great, but the environment still didn't feel as catered around as I wanted yet. So I came up with 2 new additions which would add some more depth to the environment. Firstly, low-hanging fog, and secondly, some more cumulus clouds to fill in the layer. The low-hanging fog was relatively easy to create in Houdini, but a lot of adjustment came in the later stages within the environment. I used Cloud Shape Generator to create layers moving up the side of the mountains, and used some very light billowy noise to blend the edges. Of course, as I just mentioned, within the system in Unreal, I was able to adjust the density in Engine, which was a huge help in making small visual changes, as I often found that when I made a small change from Houdini, things might look a bit too dense in some areas or too sparse in others, and this enabled me to balance things out extremely quickly. For the cumulus clouds, this one took a bit more time. I had some experience now with the Skybox node as well as the noise functions, so I then turned to the Skybox node again to generate some more sparse cumulus type clouds to hang around the cumulus layer and fill in the sky slightly between these massive towering volumes. These added a much busier look to the cloudscape. I also experimented with the wispy noise to add strandy details between the billowy puffs, which created that cotton ball look that is quite prevalent in this type of cloud. Finally came optimization. The resolution of the VDBs directly correlated to the memory usage within the scene, and a couple of weeks were spent trying to adjust some settings on the volumetric cloud component, as well as the directional light, as well as adjusting the resolution from Houdini to reach a point which was acceptable. There was and is certainly much more room for quality, but what we were trying to create is a game environment, not an offline render, and therefore we had to strike a balance of detail over performance, and I think we hit the mark. That's my segment on clouds. I hope you've enjoyed watching, and feel free to check out some of the cloud tutorials released alongside Project Pegasus, which give you a look into how I created the specific cloud types within the environment using the new Houdini 20 tools. Thank you for watching.
For the final presentation, George and Feike are going to talk about Flora, a set of prototype tools that they developed along with Tillman for foliage creation.
All right, so thanks a lot if you're still here. It's now my absolute pleasure to introduce you all to the Flora system. The Flora system is a set of tools inside of Houdini, or rather a framework for creating plants, foliage and vegetation. And it really kind of comes off of the back of years of research and development that I did into building these kinds of tools for clients and for myself in Houdini in the past. So I designed the Flora system and co-developed it along with Feike Postmes and Tillman Milch throughout the course of Project Pegasus development. And we built everything from the ground up for Project Pegasus. So why did we decide to do something so crazy? Why did we decide to sort of create this burden for ourselves of building a foliage system in a matter of months, at the same time as trying to use it to populate the world? Well, basically, that stemmed out of a dissatisfaction with the existing options. Houdini is the most powerful procedural tool on the planet. It's got the most amazing nodes, but it's kind of a little bit lacking in the vegetation department. You've got the L systems node and you've got the labs tree tools, but to tell you the truth, the L system node and L systems in general are just cumbersome, unwieldy, and hard to use. And they only really deal with the kind of growing of the structure anyway, not with the other elements of making game-ready plants. And the labs tree tools, while very cool, are more of a kind of a powerful toy than an actual suitable sort of production-ready pipeline tool that you might use in a real game production. So what is Flora? Well, Flora is a framework, like I mentioned previously, that is a sort of a node-based set of tools inside of Houdini, of course it's node-based, that allows you to describe and define the behavior of plants, but at a very, very sort of detailed level, with very explicit control over the way that the plant is behaving at every stage of its growth. We looked at the kind of direct modeling approach and the simulation style approach of modeling plants, and you can clearly see both have their strengths. The direct modeling, you have full control over what you're doing at all points in time, and with the sort of simulation-based approach, you have a very small set of parameters that can lead to a very high degree of complexity and realism. So we wanted to take the strengths of these two approaches and really marry them together, create something wholly new and sort of just better than either just on its own. And we think we've succeeded. So Flora uses the concept of delayed evaluation. So we flip the Houdini paradigm of working down on its head. And instead, what you do is ahead of time, you define the behavior of the tree through a set of modules, or the plant or the growing organism, for a set of modules. And then we have this kind of state tree or behavior tree that allows you to define exactly what the plant is doing and exactly when at every moment throughout its life. All of those instructions are then sent to a simulation kind of node or context, which evaluates that for every growing point on the tree at every step. So you have on the one hand this predetermined, pre-programmed behavior, which is explicitly controlled and directed by the artist. And then on the other hand, you have this simulation context where you're able to inject any kinds of simulation sort of factors that you might want to, such as other objects in the world, wind, and other sort of simulation elements like tropisms, figmatropism, phototropism. So all of that is built in and you kind of get it for free, and you just have a slider saying how much do I want this to stick to the explicitly defined structure that I've created for this node tree, and how much do I want specific modules to sort of throw all caution to the wind and get perturbed to their fullest extent by all of these outside factors. So of course, when you're doing all of this in this kind of context, if you grow multiple trees together and they're all interacting and competing for light and shade, you get all of those kinds of benefits like crown shyness and plants growing up other plants or on objects. So that's really the power of the simulation that we wanted to unlock. But we really didn't want the simulation to be this kind of chaotic place where the artist loses control. So we think we've done a really good job of marrying both of these two aspects together. That being said, we're still very early in the production of the Pegasus tooling. So they're very much prototype tools and we're not going to be releasing them right now to the public. But hopefully in 2024, early 2024, we'll be able to get this out there for people to start experimenting with. And I really think it's going to revolutionize the workflow of many foliage artists. So very excited to share that with you. Even though it's not ready for mass adoption, it was used for all of the plants and foliage that we created on Project Pegasus. So it's just as capable at creating trees that fit for game environments that run well and look good as it is for creating sort of high fidelity, super realistic, high production value trees for sort of pre-rendered applications. So it's really a very powerful tool. And for the future, kind of looking forwards, we'll be looking at how we can make it GPU accelerated to make things be remaining sort of real time while you're editing. Right now, it's very fast because we tried to be smart about how we built it, but we're not taking advantage of GPU acceleration yet. So that's going to be another orders of magnitude improvement. So there's lots of sort of work to be done here to really turn this into a production ready toolkit. we could give it to studios now, and I'm sure you could start using it today. But then, everyone would have their own version of Flora, and there wouldn't be this kind of one unified version that was well supported. So maybe we'll continue developing it as an open source project. Maybe we'll just be doing it in our spare time. But hopefully, it will be made a first party feature of Houdini. And now I'm going to pass you over to Feike, who's going to tell you a little bit more in detail about what it is or how it technically works. So yeah, thanks a lot.
Thank you, George. I will be going in on the technical side of the Flora toolset. As an overview, the Flora toolset has 4 core nodes: the control, component, switch, and the solver. The first 3, the control, component, and switch, are there to set up rules, and the solver is really just solving all the rules, and on a generation step-by-step basis, it's going to spawn all the components. This solver-based approach to foliage generation is loosely similar to L systems, but it's definitely its own thing with a high focus on control for the artist, but still to be generative, which means you get a lot of complexity. Right now we'll be diving into a quick example file. This is a bird tree being generated with the Flora tools. It's an example file set up by George. It exists out of 2 parts. The bottom part is the meshing stage. I won't be going in on this too much. It's basically some meshes and some leaves which are being placed and then combined. The interesting part over here is the Flora system, which is over here very linearly for this birch tree. And what you can see is that every component corresponds with a colored branch type. So we can isolate them. So right now I'm isolating component number 3, which is the origin. And let's have a look at number 4, which is this node, basically this branch, which is being placed on top of component 2. So let's have a look at component 2, because that's where previous one is being spawned on top of. And that's how you have to look at these components. They're like components of your plant. And we can add rules to these specific components. So right now you can see they're all bending a little bit downwards, and that is because over here in the simulation tab we have some gravitropism, and this is how much it listens to the gravity. So if we visualize this, we can now play with this, and for example we can move it a lot more downwards, which means that the branches will be pointing a lot more down. So let's have a look, and there we go. And that of course affects the whole shape of the tree. And that's what makes this so powerful. You have a lot of control to grab the field you want to grab and to start playing around with it. So what we can do right now is to set up our own little tree. Let's try to make something that resembles a pine tree a little. So Flora solver. And let's throw in a component, a Flora component. And once we throw this in, you can see it's pointing a little bit sideways. The UX is definitely going to get another update. Now let's move it to the middle. And let's play a little bit of these settings. So right now it's going straight up. We can see that it has 8 generations. We are controlling the amount of generations with our frames. And we can see on this component that there's a maximum of 8 generations. So after 8, it will stop. We can play around with the number of branches. So if we set this to 2, you can immediately see that it's going to explode. So every generation, basically it now tries to spawn 2. We could then, for example, move the gravitropism up a little bit and move up the gravitropism again, and immediately you can see we're getting a lot of complexity. Let's move this one back to 1, and let's right now add some kinkiness, which is adding some kink to our tree, which is all very much based in real nature, as we are twisting. Basically each generation there's a twist of 137.5 degrees, and then the kinkiness is, which is the offset, it is also rotating. So that's why it's making this weird kink, which is a very natural, organic way a plant can grow. Now let's start placing some stuff behind this. So if I place another component, Flora component, and for this node I can say right now, let's make it 2 generations. And this one, we're also gonna let it grow down a little bit so we can easily see where it lives. And right now it is being placed on each of its parent generations. So we have the main stem right now. And now we also have a child which is being placed on each of its parent generations. But we could also say that we only want it to be spawning at the end. But sometimes you want to have that control. And we could say right now we actually do want it to start branching. So there we go, adding a bunch of branches and do a little bit more. And for example, we can now say we want this one to be a little bit more flattened, because that's what we like. And you can see very quickly we are adding a shape of our tree. And then we also have a control node. I won't be setting it up right now, but basically what the control node does is that you link it to your component node, and with the control node you can make sure that a parent attribute or a driven attribute will be driving a passenger attribute. So for example, you could say at a certain height I want the branch count to be maximum of 3, or you could say I want the gravitropism, so the branch going down, only to take effect after the tree is already this large. And this gives you a lot of control to really determine the shape of your plant. This is the first initial technical overview. We're going to be releasing it with a lot more tutorials and also a lot more in-depth analysis on how to do this. Regarding the solver, we're also going to do a little bit of a tutorial regarding the problem solving steps, like how do you get to a system like this? How do you initially start creating a solver like this, which is also very interesting. And I'm just very excited to bring more of this stuff to you guys. All right.
Thank you so much for joining us today. I can't wait for you to see more over the coming weeks. We have so many more ideas for Project Pegasus, so we'd love to hear your thoughts, and we look forward to bringing you more amazing content in the future. Thank you.